So we've seen that having one bush burning 10 meters away is not going to set you on fire. But of course, when a bushfire typically goes through, there are lots of things burning, so you're going to be getting radiation coming at you from all sorts of different directions. So here's an example of a fire when there are lots of things burning all around you. So how do you work out how much heat is hitting a particular surface in this situation? And it turns out there is a very neat mathematical way to do it. Now you might think the simplest way would just be to integrate, take everything that's burning and just add them all up. And you can do that if you want to, but it will get quite cumbersome. But there is an easier way, and one that gives you more actual insight so that you can immediately see a situation and see how dangerous it is. And that's using the concept of solid angle. Now you may or may not be familiar with this. The solid angle is like a 3D equivalent of a normal angle. You know the normal angle in radians is equal to the circumference divided by the diameter. The solid angle is equal to the area divided by the radius. So an entire sphere, that's the area of 4 pi r squared, divided by the radius squared, r squared, gives you 4 pi steradians. So that's the unit of solid angle. So if all directions together is a solid angle of 4 pi steradians. So a pi steradians is 1/4 of the entire 360-degree angle around you. So it's a measure of solid angles, so angle all around. So for example, if you're taking a photograph, you can say what solid angle are you photographing? What fraction of the entire sphere of all possible directions around you is being covered? Now let's consider the heat you're receiving from two different burning areas, A1 and A2. Now A1 is smaller than A2, but it's closer to you. So the solid angle as observed by you over here is the same. Solid angle is this area divided by distance squared. So what's happening is the nearby area is smaller, and the further, more distant one is larger, but they both subtend the same solid angle. The size will be proportional to distance squared, because as you can see here, if you go further away, it has to be bigger to cover the same solid angle. So what that means is a burning area that covers, so let's say you see two burning regions and they both cover the same solid angle as you see it, the further away one must be larger. Because it's larger, and they emit a certain amount of power per unit area, it radiates more power. So the total power is going to be proportional to d squared. So again, we're seeing two different regions which cover the same solid angle, and one's further away, therefore it must be larger and therefore burn more power. However, the inverse square law tells the actual flux you receive goes as 1 over d squared. So that cancels out. Something that's further away is giving you more flux, but that flux has to travel further to reach you. So in fact, it turns out that the amount of energy you get from something does not depend on the distance. If it covers a particular surface area with fire, it doesn't matter how far away it is. If it's far away, it must be big. If it's nearby, it must be small. But either way, the total amount of flux you get, energy heat per unit area that hits you, is exactly the same. So what this is telling you is that all that matters in working out how badly a given object is being affected by fire is the solid angle it subtends. What fraction of the entire sphere, as viewed from that particular object, is covered with burning material. This actually applies to anything that is bright. It's well known to photographers. It's a concept of surface brightness. Here, for example, is a flight of stairs just outside my office, and the bottom stair is much closer to me than the top stair. But if we enlarge the pictures of the two, we'll see the brightness per pixel is about the same. The reason is that they're illuminated by the same sunlight. The one that's further away, the light has to travel much further to reach me from the inverse square law, which you'd think would make it fainter. But also because it's further away, it appears smaller. It subtends a smaller solid angle, and the solid angle it subtends also goes down as r squared. So if you divide one by the other and get the brightness per unit solid angle, which is what brightness per pixel is, it comes out about the same. This is well known to astronomers because it means that galaxies, when they go further away, they appear smaller, but the brightness per pixel remains the same, so you can still photograph galaxies at enormous distances. Okay, so let's go back to bushfires. let's imagine we've got a piece of wood over here and there's an area on the side, and we want to see how much heat that's going to receive. And let's completely surround it with flames at some temperature T. Now the flames don't all have to be at the same distance, some of them can be nearby, some can be far. All that matters is if you were sitting here, every direction you look out you will see some flame. So they cover the entire solid angle you can see from here, which is actually a hemisphere, half a sphere, so it's 2 pi steradians. Now we're going to do another trick here. Let's assume that everything is in thermal equilibrium. It's not, but let us imagine that our surface here was the same temperature as all the fire. In that case, the energy coming in and the energy coming out would be in balance. It would be thermal equilibrium. So what that means is, as a shortcut for working out how much energy comes in from all the fires, is it must be the same as the amount of energy that comes out from this region if that region was at the same 1100 degrees the fires are at. It's not, but if it was, it would be equilibrium, and that tells us that the heat in and the heat out must balance. It's actually how you derive the whole black-body equation in the first place. So even if it's colder, it still tells us that the heat coming in to a square meter is equal to the heat that would come out if it were at the same temperature as everything around it. So epsilon a sigma t to the 4th. So it's a cunning trick. So what this tells us is that if a surface area only sees flames, so the whole solid angle, 2 pi steradians, if it's a flat surface, is covered with flames, then the power it receives from all those flames is the same as the power it would radiate if it were a black body at the same temperature as the flames, i.e. about 75 kilowatts per square meter if the flames are about 1100 degrees. So, that's your answer. You don't need to integrate over anything. You don't care what distance the fires are at and where they're distributed. All you care is, from your location, what fraction of all the sky you see, all the solid angle you can see, is covered by things that are going to burn. So if they cover the entire sky, then you're going to be receiving a power of about 75 kilowatts per square meter. But if the flames only cover half the sky as viewed from your bit of flat surface, then you get half of that, so about 30 kilowatts per square meter. So in fact we can come up with an equation that the flux received is going to be the solid angle divided by 2 pi. This is for a flat surface, so it only sees half the total sphere around you, times the Stefan-Boltzmann equation. And this has enormous consequences. I mean, generally speaking, when things are burning, the flames are about the same size as whatever's burning. So you can see the flames are about the same size as the trees. So if you want to know in a particular location how bad the radiation would be, you just stand there, look at all the things that can burn around you and work out what fraction of the whole sphere around you they cover. And if it's 100%, so for example here is a photograph I took up on Mount Ainslie, and you can see that here pretty much everywhere in the photograph is covered with things that could burn. In this case it's twigs of casuarina she oak plants. So just imagine if there's a bushfire, all this could well be alight at the same time. So you'd be completely surrounded by things that are burning. It's 4 pi steradians around you. So you're going to be getting about that 75 kilowatts per square meter, which is going to be very bad. That's 75 times the intensity of sunlight. That's going to give you hideous burns. And this is actually the major danger if you're caught outside in a fire, is the incredible radiation you get. So what you want to do is find somewhere where they aren't surrounded by things that are going to burn. So for example here, a picture I took up on Mount Stromlo Observatory, there are trees around that will burn, but I'm in the middle of a grassy open space, so the trees only cover a very small fraction of the total area around me. You can see most of it is sky and road and very short grass. And so in this case, it might only be that like 10% of the solid angle around me is covered with things that are going to burn. So instead of getting 7.5 kilowatts, 75 kilowatts, I might only get 7.5 kilowatts. That's still pretty bad, but I've got more of a chance of surviving. And if it's only 3 or 4%, I've got a very good chance of surviving. But if I'm in a location like this, it's going to be very hard. What you should do if you're caught in this is, first of all, try and find somewhere where the solid angle of things that might burn around you is as small as possible. So ideally a clearing or a beach or something like that. If you can't get away from anything that's going to burn, you should try and keep the radiation from destroying you. So they normally suggest like dig yourself underground a bit or sit in a pit or something and put a blanket over you. If you're in your car, crouch down and again put blankets or something reflective over you. That very high radiative heat, that 75 kilowatts per square meter, will only last a short time while the fire front goes through. So you want to make sure that as much of the heat as possible doesn't actually reach your body, because it could do hideous burns because of it. I mean, it can be up to 150 kilowatts per square meter, which is just 150 times bright sunlight. That's lethal. So the radiation is what kills you if you're caught out. So try and avoid it. If it's unavoidable, just try and shield yourself as much as possible by non-burning things like the side and roof of your car, or going under some water or something like that to keep yourself safe.